My name's Harriet. I hack your AI, so the bad guys can't.
Now, let's talk about how we can actually attack AI. Let's get offensive. Not that kind of offensive. We're talking offensive AI. Welcome back to my channel. I'm Harriet. I missed the boat in computer hacking, so now I hack AI instead. And I'm here to help you understand how you can secure your AI systems from attackers. So today we're talking about adversarial machine learning. The field of adversarial machine learning is how I got into AI security in the first place. After working as a data scientist for a long time in a bunch of different organizations, I started doing my PhD in 2021 in adversarial machine learning and machine learning security. And I thought, why on earth in none of my jobs had anyone ever known about this? Why had no one ever discussed adversarial machine learning before? So adversarial machine learning is the field of offensive techniques within AI security that actually looks at how we can attack AI systems. Now, the idea of hacking algorithms has existed as long as algorithms have themselves. For example, avoiding spam filters in emails, and now with social media, hacking the Instagram, TikTok, YouTube algorithm to get your content promoted. But adversarial machine learning is slightly different because this is a field that really took off in 2013 with this particular paper by Zegedy and Goodfellow, and it introduced this method that allowed you to create what's called an adversarial example that, when added to a clean image, means that a model looking at that image can't correctly predict what it's looking at. And what's important to note here is that this isn't random noise. This is specially crafted adversarial noise, small perturbations to the image that are based specifically on the model that you're trying to target, or at least a model like it. And the reason that this was very different is because the way that it creates that adversarial pattern is by taking the process through which machine learning systems learn, which is through optimization. And it uses that information to understand what makes the machine learning system the most accurate, and it uses that information to make it less accurate. Now, it can't change the model itself, but it can change the data that's provided to that model. And if it knows exactly what about that data to change, it can cause a misclassification. And not just a random misclassification, it can cause a very specifically targeted classification. You can pick what you want it to be in advance and make the model predict that. That's pretty scary when you think about all of the different machine learning models that are out there predicting stuff all the time. Are they robust to these kinds of attacks? We don't know, but we know that a lot of the open source models that are used in research settings are absolutely vulnerable and usually fall victim to these kinds of attacks at least 80 or so % of the time. It's hard to give it a number, but most of them are vulnerable. It just depends to what degree they're vulnerable. So since that original 2013 paper, so many examples followed, most of them based in the image space. So for example, using adversarial patches that hide people from person detectors. There's 3D printed turtle that no matter what angle it's rotated at, the model predicts it's a rifle, and things like stickers that can cause a misclassification. If you want to understand how these techniques specifically work, I recommend watching the machine learning episode. So MITRE, which we discussed in the cybersecurity episode, also has a matrix for adversarial machine learning, and it's called Atlas. And it lists all of the tactics, techniques, and procedures, TTPs, I might have got the two T's the wrong way around, for adversarial machine learning attacks. And there are over 100 different kinds of attacks that exist. Broadly, you can lump all of those attacks into a few buckets: disrupt, deceive, and disclose. So in disruption-based attacks, we're just trying to cause the model to not work as intended or not work at all. In a deception-based attack, we're deceiving it usually in a targeted way. And then in a disclosure-based attack, we're disclosing sensitive information from the model, maybe about the data it was trained on or about the model parameters, weights and biases. Now, because there are so many different kinds of adversarial machine learning attacks, I'll save the specifics of different attacks for future episodes. However, a really useful way of thinking about how they work is by going back to how machine learning systems work to begin with. Even though there are so many different kinds of machine learning systems, at the end of the day, it always comes back to optimization. So machine learning systems are trying to optimize the parameters, the model information that they have, their activations, weights, and biases based on having historical data and then knowing what kind of output it needs to be or what it needs to look like, whether that's the correct prediction or classification, or in a large language model, knowing what good text output looks like. And so by going over many training iterations, they continue optimizing so that the model becomes better at mapping the input to the appropriate output over time. And there are lots of different kinds of functions that are used to do this. So when a data scientist is training a model, they will usually specify what kind of optimization function you're using and the information about that gradient. So that gradient is important information for the model to keep track of so that it continues to get more accurate over time. Now, as an attacker, if I can get access to the gradient function of a model, I understand what information was fed into the model to cause it to become more accurate, and therefore I can understand what information I could feed into it to make it less accurate. And that's where these adversarial pixels come in. So I've picked a small epsilon value, epsilon in math is just any small value, as a boundary, and I'm trying to, again, optimize for the maximum perturbance I can add to this model in the form of noise, this adversarial noise, that will cause it to move over a classification boundary. So instead of predicting it's a panda, it predicts it's something else. And I'm trying to do that in the optimum way so that it disrupts the model the most, but is not too obvious to a human observer. That's that epsilon constraint. So obviously this is sort of describing it in this computer vision-based evasion use case, but you can think about it in similar ways for all the other model types as well. So the Harriet hack of the episode is to think about adversarial machine learning in terms of their ability to disrupt, deceive, and disclose information from models. And there are lots of different ways that you can do this. I recommend you check out these resources if you want to find out more, as well as future episodes that dive into specific implementations. I'm interested to know your thoughts on adversarial machine learning and any exposure you have had to it before. Please let me know in the comments. If you want to support this video, please like and subscribe so you don't miss out on future episodes. And that's all for now. I'll see you in the next episode.